In the past, we learned several techniques of integration to solve problems. This chapter is giving us several tests to figure out if series converge or diverge. So far, we've had the nth term test, and that was a test for divergence only. We've looked at geometric series, and we know they converge if the absolute value of r is less than 1. And then we've also looked at telescoping series and looked at different techniques to find out if those converge or diverge. This section we're going to be looking at the integral test, and from the integral test that's going to lead us to the p-series test. So let's get started with that integral test. So we have a sequence of infinite positive terms. Now that's kind of key, because remember, some of our sequences had negative, so this is limiting to sequences that only have positive terms. And we're going to make that sequence, of course, a function. And that function is going to be continuous, positive, and decreasing for all real values greater than or equal to 1. So no longer are we going to be looking at just the natural numbers. We're going to set that function to be a function of x. Why? Because the integral test is going to say if we take the integral from 1 to infinity of this continuous positive and decreasing function and it converges, then the corresponding series converges. However, if that integral of that continuous positive and decreasing function diverges, then the associated series diverges. We have to be very careful of notation. We have to use a different variable to indicate that we're using functions of real variables so we can have that continuity. So we're going to use the integral test to see if a series converges or diverges. And here is a real big key. In order to use the integral test, you need to state that the function is positive, continuous, and decreasing. You have to state that, and sometimes you have to prove that. So how do we get started? Well, first of all, let's just look at this series, because this is a very interesting series. If we write out some terms, we have 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 out to infinity. Now we know the terms are getting smaller, but that does not mean that the sum is converging. Now, just to let you know, this is called the harmonic series. And lots of fun-filled things can be done with the harmonic series. But let's just see if it converges or diverges. Since it's not geometric, since it's not telescoping, and the nth term test fails, let's just review that. Remember, the nth term test says the limit as n approaches infinity of the sequence has to not equal to 0. But the limit of this does equal to 0. So this test fails. It tells us nothing. So we have a different approach. We're going to use the integral test. So the first thing you're going to do is you're going to write down the words, let f of x equal to 1 over x, not n. And I'm also going to state that x is going to be only greater than or equal to 1. All right, so what do we have to say? Well, we have to say that f of x is continuous as long as x is greater than or equal to 1. That's pretty obvious. We should know what that graph looks like. It only has a vertical asymptote. Remember, when the denominator is 0, so we only get a vertical asymptote or when that function is undefined at 0, and that's not in our interval. We can also say that f of x is positive on the interval greater than or equal to 1. If it was less than 1, then we would have some negative values. But we have to show that it's decreasing. Now you might say, well, it's pretty obvious. It's getting smaller and smaller. So since it's obvious, we're going to state that. It's also decreasing on that interval of x is greater than or equal to 1. Just for sure, for sure. So how are we going to see if it converges or diverges? So we have to go back to our improper integrals. So we say from 1 to infinity of 1 over x dx is going to be the limit, and then choose some dummy variable. I'm going to choose a, approaches infinity of 1 to a. So now we get to integrate that. So that's going to be the limit as a approaches infinity. Well, how do you integrate 1 over x? That's the natural log of the absolute value of x from 1 to a. Now, truthfully, we really don't need that absolute value since we've restricted a to be greater than or equal to 1, but just kind of by habit, I put it. Okay, so this is going to be the limit as a approaches infinity of the natural log of a minus the natural log of 1. What's happening here? Well, this is 0. What's happening there? As a approaches infinity, that's going to approach infinity. So this limit does not exist, or you could say it goes to infinity. But since the limit does not exist, we would say this integral diverges. I'm running out of room, so I'm going to come up here. So therefore, the series diverges. And I'm going to even say, because I use the integral test. Okay, that was pretty easy. The reason why it's easy is because you could just state those three. They're very obvious. What happens when it's not as obvious? Okay, so once again, the nth term test is going to fail because the limit of that goes to 0. That tells us nothing. It's not geometric. It's not telescoping. So let's try the integral test. So I'm going to say let f of x equals to 1 over x squared plus 1 for x greater than or equal to 1. You have to write that. Okay, what else do I need to state? I need to say that f of x is continuous and positive on the interval x is greater than or equal to 1. I don't think you're going to have any arguments there. It's continuous because the domain is all real numbers, and it's positive because you have x's squared and x's are all positive, so that's all good. The question is it decreasing? And you're saying, well, sure, that's really obvious. Well, pretend that it's not. How could you show that it's decreasing? So how can I show f of x is decreasing? Of course, find the derivative. So that's what I'm going to do. So using the, let's use the quotient rule. Why not? You could not, but I'm going to do that. So I'm going to have the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. So that's 0, so I have negative 2x over x squared plus 1 squared. So I need to show that that's decreasing. Decreasing means that the derivative would be negative everywhere. Okay, so we know that this is always positive. Well, what about that? Is that always negative? Well, yes, because it's always negative if x is greater than or equal to 1. Remember, if we had some negative values for x, it would be positive. But since this is negative and that's positive, negative divided by positive is negative. So we've now shown that f of x is also decreasing as long as x is greater than or equal to 1. But we've still not done the integral test. So we have to now do the integral test. So if I have from 1 to infinity of 1 over x squared plus 1 dx, I'm going to rewrite that as the limit as a approaches infinity of my integral. Then I have to remember how to integrate that. And hopefully you're saying, oh yeah, that's arctan. So I'd have the limit as a approaches infinity of the arctan of a minus the arctan of 1. Okay, so we have to know what that is. What angle gives you a tangent value of positive 1? Do you know that? You should. That's pi over 4. But what about here? And you're saying, well, a approaches infinity. That's true. So think about your tangent graph. When does tangent approach positive infinity? What angle is it getting closer and closer to? Pi over 2. So pi over 2 minus pi over 4 is pi over 2. So does my integral converge or does it diverge? My integral converges. So therefore, I can say that my series converges by the integral test. Okay, now let's talk about this. Just because the integral converged to pi over 2, that does not tell you that the sum of the series is pi over 2. They do not necessarily converge to the same value. All right, so let's just practice that one more time. If I said use the integral test, what's the first thing you're going to write down? Yes, you're going to write down let f of x be a function of x. And then you're going to state, hey, f of x is continuous, it's positive. And why is it continuous? Because there's no vertical asymptotes. That domain is all real numbers. It's positive because all of our x values are positive. Okay, and then I'm going to ask you to show that it's decreasing. And I'm going to do that by taking the derivative. So the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. So let's see, this is going to be x squared minus 2x squared. So I'm going to have a minus 1x squared, and then I'm going to have a positive 1. Let's just check that arithmetic again. That's x squared plus 1 minus 2x squared. Okay, that's good. So this denominator's always positive. The question is, what about that? Is that always negative? Well, this is always negative as long as x is greater than or equal to 1, right? If it's, is that true? Not greater than or equal to 1, but it is always negative for things greater than 1. So it is eventually decreasing, and that's fine. And so now we can say f of x is decreasing on the interval x is greater than 1. So now we're going to apply the integral test. Then we have to remember how to integrate that. Well, let's see. If I let u be x squared plus 1, du is 2x dx. And so this becomes 1/2 the integral of du over u, which of course is the natural log function. So to finish this up, this is going to be the limit as a approaches infinity of 1/2 of the natural log. And again, I'm putting those absolute value bars, but you don't really need to because, again, we're in positive land anyway. So let's see, we have 1/2 the natural log of a squared plus 1 minus the natural log of 1 plus 1. So that's a finite number. But what happens as a approaches infinity? This goes to infinity. So we can conclude that the integral diverges, therefore our series diverges. And that's, once again, due to the integral test. Now I said the integral test would lead us to the p-series.